Here we go again. I'm jumping right into the next integration video, Introduction to Integration and Applications, Part 2. Now, in the first video, those were all just plain integrals. None of it was, we hadn't started any applications. The applications are going to kind of start from here. All right, so the first application is formulating the equation of a curve from the gradient function dy dx. Okay, let's see if this makes sense. If dy dx is equal to some function of x, it implies to get back y. Remember, you had to differentiate some function to get dy dx. So therefore, if I dy dx, which is f of x, if I integrate back that dy dx, or integrate that f of x, then I'll get back y. In fact, let me spell it out even a little better here. That means to get back y, I have to integrate dy dx with respect to x, which means integrating f of x. And that will give me some g of x plus c. Y equals g of x plus c represents a family of curves depending upon the value of c. Now, c can have different values depending upon what point or points the curve passed through. An xy coordinate pair must be given to find the specific curve within the family of curves. All right. So why don't we look at our first example? Right? So if you're given a dy dx function and asked to find back the equation of a curve, then obviously you go back in the opposite direction. From dy dx, to get from dy dx back to y, you would need to integrate. Kind of makes sense. Let's look at our first example. We're jumping right in. Now that we know how to integrate, right, indefinite integrals, now that we know how to do that, we should be able to handle this. So the gradient function of a curve at a point xy is given by dy dx is equal to 1 upon the square root of 1 minus 3x. Find the equation of the curve given that it passes through the point with coordinates minus 5, minus 2. Okay, so you're given dy dx and you want to find back y. How do you do it? Well, we're going to start by saying if dy dx is equal to 1 upon the root of 1 minus 3x, that implies that to get y, you need to integrate that dy dx function, the 1 upon the root of 1 minus 3x dx. Okay, can we integrate that function? Of course we can. This would be equal to the integral of, y would be equal to the integral of, I want to write that as 1 over 1 minus 3x to the power of a half, and then dx, and then throw the 1 minus 3x to the half up into my numerator, and that becomes the integral of 1 minus 3x to the power of minus a half dx. Oh my, excuse me. Be right back. Sorry about that. Yes, where was I? I'm now integrating a function of the form integral of f of x to the n, where f of x is linear and n is not minus 1. You would remember those rules from before, or that rule from before. what would I end up with in that scenario? Well, you'll end up with 1 upon f prime, or 1 upon the derivative of what's inside the brackets, 1 upon minus 3, into 1 minus 3x to the power minus a half plus 1, which is a half, divided by minus a half plus 1, which is a half, plus c. So let's see if we can tidy that up a little bit. Y is equal to, if I upturn and multiply by the half, I'll get 2. 2 times minus 1/3 is minus 2/3. And then the 1 minus 3x to the half I'll rewrite as the root of 1 minus 3x. And then plus c. There. Now, the only way, this represents a family of curves like I said above. The only way I can find this specific curve is if I know a point through which the curve passes through. And they told me the curve passes through the point with coordinates minus 5, minus 2. The curve passes through the point with coordinates minus 5, minus 2. Which means I can plug in the minus 5 for the x and the minus 2 for the y. If I did that, I will get minus 2 is equal to minus 2/3 times the root of 1 minus 3 times minus 5 plus c. Let's simplify that. Minus 2 is equal to minus 2/3. Okay, what's under the square root? The minus 3 by minus 5 is minus 15, plus 1 is 6. Sorry, minus 3 by minus 5 is 15, plus 1 is 16. Square root of 16 gives me 4 plus c. Minus 2 is equal to minus 8/3 plus c. C, making c the subject, c would be a positive 8/3 minus 2, and 2 is 6/3, which gives me 2/3. So now that I know the value of c, I can plug it in here and find the actual curve. So finally, y is equal to minus 2/3 times the root of 1 minus 3x plus 2/3. Like that. You can tidy this up a bit. You have a common denominator. And I'll spin it around. I'll put the piece with the minus in the back. So y would be equal to 2. Oh, I can factor out the entire 2/3. Y is equal to 2/3 into 1 minus the root of 1 minus 3x. I gotta be right back. Oh gosh, I'm getting a sneezing fit. Sorry for the delays. Alright, let's keep going. So that's the equation of the curve we end up with in that case. Let's try the next one. This one says the gradient function of a curve at a point xy is given by dy dx is equal to 3 cos x. Find the equation of the curve given that it passes through the point with coordinates pi upon 4 and 4 upon root 2. So we're going to start off the same way again. If dy dx is equal to 3 cos x, that would imply that to get back y, I have to integrate the dy dx, which means integrate 3 cos x. And of course I have to put dx there. And therefore y would be equal to, well, remember what you get when you integrate cos, you just get sine. So 3 sine x plus c. Can't get any easier than that. But the curve passes through the point with coordinates pi upon 4 and 4 upon root 2. So if we plug in, I hope you all remember your surds. The y coordinate is 4 upon root 2. We'll get 4 upon root 2 is equal to 3 sine, and the value for x is pi upon 4 plus c. 4 upon root 2. I'll rationalize that one time. Times root 2 upon root 2 is equal to 3 times sine of pi upon 4 is root 2 upon 2 plus c. Yeah, we gotta get to trigonometry pretty soon, right after integration. All right, so here, what do we have? This is on the left hand side. It's 4 root 2 upon 2, which is just 2 root 2, is equal to 3 root 2 upon 2 plus c, which makes c equal 2 root 2. Maybe I should have left it as 4 root 2 upon 2. Make my life easier. So on the left, I have 4 root 2 upon 2 is equal to 3 root 2 upon 2 plus c, which makes c equal 4 root 2 upon 2 minus 3 root 2 upon 2. And everybody can do that subtraction. Even I could do that subtraction. Because 4 root 2 upon 2 minus 3 root 2 upon 2, it's like 4 apples minus 3 apples, giving you 1 apple. 1 root 2 upon 2. So c is just root 2 upon 2. And if I take the value of c and plug it back in here, I have this specific curve. So I end up with y is equal to 3 sine x plus root 2 upon 2. That is the equation of the curve that they were asking me to find, whose gradient function was 3 cos x. If I leave it with the plus c, that's a multiple curves. I have to actually find, I can give any pair of coordinates and I'll get a different value for c. And each one of those will represent a different curve. So that's why it's a family of curves. If I had given x is pi upon 2, y is 6 or something like that, I would end up with a different value for c and therefore a different curve. Okay, so that's that example. Now, I picked a problem from last year's 2019 math paper, because the students came out and cried, I don't know what kind of problems people give, so I don't know. They gave the easiest problem in the world. Y'all don't still get licks though, because you should have been able to master this. Y'all know who I'm talking to. I ain't calling nobody name. No names called. Okay, it's actually problem number 5 on the advanced paper. I actually wrote it right there. Paper 2, 2019. Here we go. This problem actually combines stationary points with dy dx and integration. Puts the whole story together. The stationary points on a curve are given as 5 and 11 2/3. They're very seldom, if ever, used mixed numbers, but it looks like they use it here. And 3 and 15, the stationary points. Okay. First thing they ask you is to derive the expression for dy dx. And they gave 2 marks for that. The first thing you should be writing here is this. So for part A, at a stationary point, dy dx must be equal to 0. So, how did we get this coordinates of the stationary point? We had to take the dy dx expression, equate it to 0, and then solve for x. Okay. Now, it's obvious that the x coordinates of the stationary point are 5 and 3. So, x equal 5 would be one x coordinate of a stationary point, and x equal 3 would be the other. Which means I could turn that expression into a factor. X minus 5 equals 0 would be one factor, and x minus 3 equals 0 would be the other factor. Which means if I multiply x minus 5 times x minus 3 and equate that to 0, that would represent my dy dx expression equal to 0. So they want the dy dx expression. I'll simply write dy dx is equal to x minus 5 times x minus 3. Because remember, you have to set dy dx equal to 0 and solve for x to get the x coordinates of the stationary points. So if I reverse that process, I should be able to get my dy dx. So that wasn't so difficult. Take the x coordinates of the stationary points, create the factors. From the factors, create the dy dx expression. 2 marks. That's worth 2 marks. What's the next thing they were asking me to do? The next thing they were asking was determine the nature of the stationary points. Well, first of all, let me expand this out. Dy dx is equal to x squared minus 5x minus 3x is minus 8x plus 15. Everybody knows to determine the nature of the stationary point, you need the second derivative, am I right? D squared y upon dx squared is equal to 2x minus 8. We could do that in our sleep. I know all y'all can. That's the second derivative. And you test your stationary point by plugging in the x coordinate of the stationary point into the second derivative. So the first stationary point has coordinates 5 and 11 and 2/3. So at the stationary point, 5 and 11 and 2/3. I hate writing numbers like that. D squared y upon dx squared is equal to 2 times 5. You plug in the x coordinate minus 8. 10 minus 8, that's 2. When the second derivative is positive, you end up with what? A minimum stationary point, which makes 5 and 11 and 2/3 is a minimum. Then we check the other stationary point, which is 3 and 15. At the stationary point 3, 15, d squared y upon dx squared. This time you plug in x equal 3 into the second derivative. 2 times 3 minus 8, 6 minus 8, which is minus 2. Since the second derivative is negative, then the point with coordinates 3 minus 15 is a maximum stationary point. The third part is determine the equation of the curve. Part C, determine the equation of the curve. Remember, to get the equation of the curve, you would have to you would have to integrate the dy dx function. Give myself some space here. So let's write back dy dx, which was, in the expanded form, it was x squared minus 8x plus 15. Y'all need to check out my algebra and that stuff here, So to get back y, the equation of the curve, I need to integrate the dy dx function. X squared minus 8x plus 15 dx, which gives me x cubed upon 3 minus 8x squared upon 2 plus 15x plus c. Let me write that back here and simplify it a bit. Y is equal to 1/3 x cubed minus 4x squared plus 15x plus c. And now they gave me 2 points through which the curve passes. Both are stationary points. The curve has to pass through those stationary points. So I could pick either one and use it to find my c. I'm going to pick the 3 and 15. So the curve passes through the point 3 and 15, which is obviously is a stationary 3 and 15, which is a stationary point. Therefore, if you cater for that, y is 15 is equal to 1/3 times 3 cubed minus 4 times 3 squared plus 15 times 3 plus c. Okay, 15 is equal to, what do I have? 3 3s, 9 3s, 27 over 3, which is 9. Bring it back to 9 minus 9 4s is 36 plus 15 3s is 45 plus c. And I don't feel like adding the numbers in my head. Getting like y'all. Oops, no shade. 15 plus 36 minus 9 minus 45 equal minus 3. C is equal to minus 3. Let me double check mentally. 45 plus 9 is 54. 54 minus 36. 46, that's 18. 15 minus 18 is minus 3. And therefore, the equation of the curve is y is equal to 1/3 x cubed minus 4x squared plus 15x minus 3. Voila. All right. So this is an example in which you have to go in both directions. You have to take the dy dx, differentiate that to get the second derivative to determine the nature of the stationary points. Then you have to take the same dy dx and integrate it to get back the equation of the curve. What you should do, I'm not going to do it, but you should do it for your own benefit. Take the other point, take the other stationary point and plug it in. You should get exactly the same value for c. If you don't, then there's some error somewhere. I made an error, though I doubt it. Right, plug in. Where's the other point? Plug in the point with coordinates 5 and you change that to a mixed number, an improper fraction. That would be 11 3 is 33, 35 over 3. Plug in. Forgot 3 and 35 over 3. 5 and 35 over 3. Yes. 5 and 35 over 3. Plug in 5 for the x and 35 over 3 for y. Crunch. You should get exactly the same value for c and therefore the same equation for the curve. All right. So that takes care of that application. Now we're going to switch to definite integrals. Been talking about it all along. Definite integrals. What's a definite integral? The definite integral over an interval AB is equal to the difference between the antiderivatives evaluated at B. Antiderivative, let me read the entire thing again. The definite integral over the interval AB is equal to the difference between the antiderivative evaluated at B and the antiderivative evaluated at A. Notice when I write an interval like this, AB, in square brackets like this, which are really brackets. These things are parentheses. When I write it in brackets, I'm talking about two different x values. Let's say x equal a and x equal b. That's what I'm talking about. But when I write this AB, I'm talking about a pair of coordinates, x and y coordinates. So it depends upon the context in which you use it to. So whenever I say an interval AB in square brackets like that, it means a lower value or a lower limit or a lower boundary of A, a lower x value of A, and an upper x value of B. So how do you write the definite integral? Well, if you're integrating a function, some function f of x, with respect to x, f of x dx, then you write the limits or the boundaries as shown there. The lower boundary or the lower limit is shown at the bottom here, shown at the bottom of the integral, and the upper boundary or upper limit is shown on top there. I'll be right back. Nose. Okay, I'm back. Yes. Okay. Now, whenever you integrate a function, some function f of x, you get some result g of x, and if it were an indefinite integral, you would have a plus c. If it were an indefinite integral, you get a plus c. For a definite integral, there is no plus c. And what you do, you evaluate the function between b and a. What does that mean? You plug in the upper limit into the integral, so you'll get g of b. That should be into the antiderivative. You get g of b minus, you plug in the lower limit, and you get g of a. A is your lower limit, b is your upper limit. Or boundary. Sometimes they use the word boundary. There. Okay. So it's not difficult to evaluate a definite integral. And I have several examples here. We're going to just jump right in. Let's look at the first one. The integral of 4x squared plus 6x minus 7 dx between limits 0 and 1. That's how you read it. Let me read it again. The integral of the function 4x squared plus 6x minus 7 dx between limits 0 and 1. Okay. Well, you will integrate that function the same way you would integrate a regular polynomial by using the rule for f of x, the rule for the integral of ax to the n dx. So this will give me 4 times x to the 2 plus 1 over 2 plus 1 plus 6 times x to the 1 plus 1 upon 1 plus 1 minus 7x. There is no plus c, but you will simply evaluate this expression between x equals 0 and x equals 1. How do you evaluate between 0 and 1? So this vertical stroke means evaluate that function between 0 and 1. You plug in the upper limit first. So this would be 4 thirds times 1 cubed plus, well, 6 upon 2, that was between 3 times 1 squared minus 7 times 1, and then minus what you get when you plug in the lower limit. Well, if you look at it, because my lower limit is 0, I will get 0 everywhere. So that entire lower limit gives me 0. And I simply evaluate everything in there. 4/3 plus 3. Let me see, this is 4/3 plus 3 minus 7. 3 minus 7 is minus 4. Minus 4 is minus 12/3. 4/3 minus 12/3 is minus 8/3. So if I were to summarize, yes, if I were to summarize the definite integral of 4x squared plus 6x minus 7 dx between limits 0 and 1 is negative 8/3. Negative 8/3. Okay, that's that one. There we go. All right, let's go on to the next one. Yes, the integral of a half x minus 3 to the power minus 2, that should be a dx there, between limits minus 1 and 4. Well, let's apply the regular rule. Well, this is not a regular rule. This is of the form. This function is in the form f of x to the n, isn't it? It's in the form f of x to the n, where f of x is linear. Half x minus 3, that's linear. And n is not minus 1. Under those conditions, the result is 1 divided by f prime. F prime would be a half, so 1 divided by a half, into f of x, a half x minus 3, to the power n plus 1, minus 2 plus 1, which is minus 1, upon minus 1. Evaluated between minus 1 and 4. Now, this one is a little more interesting. The 1 divided by a half, if I flip the half, I get 2. So it's 2 times 1, which is 2. And the minus 1 will float to the top. So I'll just have 2. And I'll throw this guy on the bottom. A half x minus 3 to the power positive 1. Evaluated between minus 1 and 4. Hope you saw what I did there, right? Hope the algebra was not beyond you. 1 divided by a half, that's 2. The minus 1 that you're dividing by, 2 divided by minus 1 is minus 2. I forgot my minus. It's minus 2. And the half x minus 3 to the minus 1, I threw it in the denominator to get just half x minus 3 to the positive 1. Okay, what happens here? Just plug in my limits. When I plug in my upper limit, what do I get? Minus 2 upon a half by 4 is 2. 2 minus 3 is minus 1. So that's what I get when I plug in the upper limit, minus what I get when I plug in the lower limit. Let me check that back. 4, half of 4 is 2. 2 minus 3 is minus 1. Minus 2 over minus 1. Yes, and then this becomes minus 2 on top. When I plug in minus 1, a half times minus 1 is minus a half. Minus 3. Minus 3 is minus 6 halves, which is minus 7 halves. Gosh, this thing gave me a good workout on my fractions here. All right, so I'll get 2 in front. Looks like I get 2 in front there. And minus, and flip the the minus 2 over minus 7 halves, that's a plus. So flip the 7 halves, I get 2 sevenths. So this looks like it's 4 sevenths. 2 is 14 sevenths minus 4 sevenths is 10 sevenths. You have every opportunity to check my algebra and my arithmetic and my calculus and everything all together in this one. All right, so therefore the integral between minus 1 and 4 of a half x minus 3 to the minus 2 dx is equal to 10 sevenths, I think. I don't think I made any mistakes there. Okay, and I have one more. Yeah, okay. All right, and the last one, the definite integral of 2 sin x plus 3 cos x dx evaluated between 0 and pi upon 6. So let's find the indefinite integral first, or the antiderivative as they call it sometimes. When I integrate sine, I get minus cos, right? So this would be minus 2 cos x plus 3. When I integrate sine, I get positive. When I integrate cos, I get positive sine. So minus 2 cos x plus 3 sine x. And I have to evaluate that entire thing between 0 and pi upon 6. All right. Plug in the upper limit first. Minus 2 cos of pi upon 6 plus 3 sine of pi upon 6. That's what I get when I plug in the upper limit. Plugging in the lower limit, I get minus 2 cos of 0 plus 3 sine of 0. Okay, pi upon 6. Cos of pi upon 6, I think that's a third. That's root 3 upon 2. Y'all can check it on your fancy calculators. Minus 2 times root 3 upon 2 plus 3 times, and sine of pi upon 6 is a half. 3 times a half. Minus into cos of 0 is 1. Sine of 0 is 0. So that would just leave me with minus 2 inside there. Okay, let's tidy this up. This would be I'll write this fraction first. I'll write the 3 halves, and then minus root 3, because the 2's will go right there, just root 3, and then plus 2. Minus and minus gives me a plus 2. So minus root 3 and plus 3 halves. Okay, 3 halves plus 2. 2 is 4 halves. 3 halves and 4 halves is 7 halves. That's 7 halves minus root 3. If I write it as a single fraction, 7 minus 2 root 3 upon 2. So, summarizing, integral between 0 and pi upon 6 of 2 sin x plus 3 cos x dx is equal to 7 minus 2 root 3 upon 2. There is no plus c when you do the definite integral. You simply evaluate the function between the given limits. There. And that's that application. Finding definite integrals. Now we're going to use the definite integrals later on to do things like finding areas on the curves and volumes of solids, which is the next video. All right. I gave you more problems in this case. Same Riemann Tulsi text. And here are the problems that I've given. So go to it. I will now call this video to an end and move on to the next one. So that's the end of this one. I'm out.